Everybody, we are live. Hey, how's it going? We are live. Feeling alive. It's
Alive.
Saturday. I got Mark on here with me. What's going on, Mark?
Hello, everybody. It's a beautiful day, beautiful Saturday morning.
Yes, it is. So, we're excited to share this with you. Just some general housekeeping items. People are going to trickle in as this goes live longer, but as you're coming in, feel free to be active in the chat room. I will make sure I'm monitoring those questions. So Mark's going to have his head in a book, and sometimes he doesn't see
Yeah.
those.
Yeah, I'll have my head down working these things. So Isaac will clue me in on any questions. But today we're going to get into essentially a set of not only breadth problems that you might see on either one of the tests, the FE or the PE, but we're also going to get into some more of the depth type problems. And all these are geared towards construction engineering. So, um, with that, should we get rolling, Isaac?
Yeah, I would just give a note to people if you are joining and you're not part of Civil Engineering Academy, part of our community, you can join our free Facebook community at ceacommunity.com. And if you're not a member of any of our courses, we have tons more video practice problems in there with lectures and exams and support. If you need the FE, go to civilfereviewcourse.com. And if you need the PE, go check out civilpereviewcourse.com. And so if you have any questions, feel free to email us. You can email me, Isaac, ISAAC, at civilengineeringacademy.com, and I'm ready to help you. So I
Yeah.
think with that, Mark, I will let you go at it and get started solving some of these problems.
Okay. So I need to share my screen. So let's go ahead and do that. Okay.
Okay, let me add
Every,
this to our stream, and off you go. There you go.
everybody see that? Okay, here we go. So our first problem, it deals with a concrete specialty subcontractor. Ooh, that sounds like a fun deal. Let's see what that's about. It says a concrete specialty subcontractor has historical data showing that one wall crew of 5 people can execute 800 square feet of wall formwork in one day. If 2 wall crews are used, what is most nearly the number of days it will take to execute 150,000 square feet of wall formwork? Okay. Pretty straightforward. If we kind of get the basics, that duration, if we're talking about duration, it's going to be our quantity. Oop. That's supposed to say quantity divided by our productivity. So in this case, we can take our 150,000 square feet of formwork that we have to execute, and then we're going to apply our productivity, which we're told in the problem statement is 800 square feet per crew day. And then there's 2 crews. So we got to times that by two crews. And we'll extend that line out. So if we look at the units on this, crews cancel out, square feet cancel out, and we're left with just days. And if we grind through that calculation, like I said, it's pretty straightforward. We should come up with 93.75 days. And in a practical situation, we'd probably round that up to 94 days. So with that crew, those 2 crews working wall forms, we could say it's going to take them 94 days to get all that stuff done. And that goes a long way in helping schedule that operation if you were working on a schedule for your formwork. So pretty straightforward. That would be more of a like I say, more of a breadth type question that you may encounter in construction engineering. Isaac, is there any questions on that one?
Let's ask. Does anybody have any questions on on this duration on how to do this estimate? Probably give it a second here. I know there's some lag time between doing these things live and actually people asking questions, but so far no questions. We do have
Okay.
quite a few people watching, which is nice, and so
Yeah, it's durations are fairly straightforward. You're always working with a quantity, which could be, a square footage, and then you're dividing by a productivity, which at the end of the day generates hours. We can call those person hours. In this case, we were using a crew and the number of days that they were going to perform, which you could say if there's 8 hours in a day, it could boil down to, a crew of two crews could be executing, about 8 hours worth of work per day. But when you're talking about a duration, you're usually in the practical world, you're working with a unit like square feet, and then you're dividing it by a production rate, which will be square foot per person hour, something like that. And then you're left with person hours. And from that, depending on your crew size, you can generate the number of days that are required for a certain operation.
I
It's
guess
another
the
way to look at it.
question is there any other problems that could be generated out of this that they uh, something else they would have to solve for that could come out of a question similar to this?
Well, it could be maybe they're going to be placing concrete. I mean, just because we're dealing with form work, this could be anything. We could say this crew has 1,000 cubic yards of concrete, right? And we know, and if maybe they're in a wall form, and we know that this wall form, maybe we've done our heuristics, we know our historical data. We think we can place 5 cubic yards per person hour on that wall. Using that type of information, we could say, 1,000. If there's 1,000 cubic yards, we would divide that by 5, cubic yards per person hour to come up with how many person hours it would take to do that, right?
Mark,
And
there is
then,
one question on that equation you wrote up there for duration.
uh-huh.
There's confusion on what was written on the numerator there.
So that's 800 feet squared per crew day, right? We were told that 5 people, and it's kind of interesting because sometimes in problems they give you extra information. We don't really need to know how many people are in the crew. We just know that one wall crew, can execute 800 square feet per day, right?
Well, when your equation that says duration equals something over productivity.
Oh, yeah, I'm having a little. This is quantity.
Oh,
Sorry, my pen is acting up
that's
right
looking
there.
messy.
Yeah, it's messy. This should
That's
be.
quantity.
This
Ivy asked that. She thinks it says eighth time over productivity.
No, it's Q. I'll abbreviate it as QTY divided by productivity. And
Perfect.
so I've extended that out as we go to the right to 150 square feet divided by the production rate of the crew, the 2 crews.
That helps.
Okay.
Just in general, just so you know, we've got a mix of people here. Some taking the FE, some taking the PE. A lot of people taking their exams in April. So, just getting a nice mix of people studying for their exams. And these are problems you will see. This type of problem you would see on both
Yes.
kind of exams. So,
and this would be kind of a breadth type problem because it's fairly straightforward once you get the concept. So, Okay.
Cool. No other questions on this one, so let's
We're
jump
going to
to your
move
next
on to
one.
problem 2. So here's another one that would maybe be a breadth type question. So this one's more of a scheduling type question. It says a drainage contractor has been awarded a new project. He is contracted to install 1,000 feet of 12-inch diameter drainage pipe buried 5 feet deep into the ground. The contractor has asked you to help schedule the time it will take to execute the work using a table of historical scheduling data from similar projects and assuming an 8-hour workday. What is most nearly the total duration in days for the contractor to complete the installation of the 12-inch drainage pipe? And we've got a little table here that really represents a schedule. So the first activity on that schedule is excavating the trench, and that's going to take 16 hours. Place bedding material in the bottom of the trench. The predecessor is excavate the trench, right? And then we've got 8 hours to perform that task. Next in line is we place the pipe. Then we get the bedding as the predecessor, right? That precedes the actual placing of the pipe. That takes 6 hours. Then we backfill the trench once the pipe's in place. And the predecessor to that was placing the pipe. Now, this isn't presented in like a Gantt chart format. So we're to assume that there isn't any lags or overlaps, right, in our schedule. So if we were to draw maybe a little Gantt chart just to make this more explicit, if I had my excavation and my little Gantt chart, I had my little duration line going like this, right? And this was 16 hours. And then I had my bedding, let's say. That would start after this one ended, and then it would go on for 8 hours. And then let's say this is my pipe, place pipe. That one's going to start out here and go zoop for 6 hours. And then here's my backfill. And that's if I were to extrapolate this data into more of a Gantt chart, which sometimes intuitively makes a little more sense, right? Just visually. And so if
Yeah,
I
you can see the overlap if there's any scheduled overlap.
So in the problem statement, we're not told that there's any overlap. One task kind of goes into the next, and we're to find out what the duration is in days. Well, once you lay it out like this, you can see, oh, I just got to add up all these hours. How hard is that, right? So 16 plus 8 plus 6 plus 10 equals 40 hours. And then we divide that by 8 hours, right, per workday, per day. And so our final answer, 5 days. Pretty straightforward. But I think once, even though the information is presented in a tabular kind of a format, I think it makes sense to draw that out. And you can kind of visualize how there isn't any overlap, and then you realize it's just additive. If there had been some overlap, let's say that, the bedding maybe could have started in here, and maybe it was 10 hours or something, right? Then you know that the outside duration on that one would have been 8 hours, and this maybe would have been 2. And so the cumulative effect would just be to add 16 plus 8 plus 6 plus 10 if there was any overlap. Just as an example of that type of information. So pretty straightforward.
If you had any other activity like backfill that worked in parallel with any of those,
yes,
you can see that real quick.
And in real life, that's probably what would happen. They would probably start the pipe, laying the pipe, and then they'd go back and start the trenching. So backfill may really start back here, right? And come out to this point and maybe end right there for the 10 hours in reality. And then you'd only have 4 hours that were outside of this 6-hour task of laying the pipe. And then you'd have 4 plus 6 plus 8 plus 16. So it really helps in my mind to lay it all out in kind of a Gantt chart format like this, and then you can visualize what you've got to do. So hopefully that's fairly straightforward to everybody. Any questions, Isaac, on that?
Any questions popping up on this guy? I think this one's relatively straightforward if you understand a little bit of project scheduling. If you do have questions, pop them in the chat box, and we will get to them. But right now, I think this one was pretty straightforward for people.
Okay, this one's going to be a little more involved, so let's get into it. This one is talking about a concrete placing operation and analyzing how much time it's going to take and then figuring out a cost. So it says a general contractor is building a new office building requiring the installation of 2 new electric generators that are to be placed on top of 4-inch thick concrete housekeeping pads. Given the location of the pads, it is determined that using the tower crane and a 2 cubic yard concrete bucket is the best way to pour the pads. A 5-member concrete crew is required for the work. 1 person will be at the concrete mixer truck, 3 will be placing and finishing the concrete, and 1 will be running the concrete vibrator. The average regular wage rate for the crew is $25 an hour. Overtime rate is 1.5 times the regular rate and becomes effective after 8 hours of work. The time needed to pour the housekeeping pad is estimated at 25 minutes of setup time, 10 minutes for each pour cycle, which is made up of 4 minutes to load the concrete in the bucket and then 6 minutes to swing the bucket, dump the concrete, and then return for more. And then cleanup and demobilization time will take 20 minutes. If 110 cubic yards of concrete needs to be poured, what is most nearly the labor cost per cubic yard of concrete for placing these pads? So this one's got a lot of information. What I would advise, first of all, is kind of visualizing the operation that has to happen here. So we've got a concrete bucket. It's got to be loaded up with concrete. Well, first of all, they got to get everything set up, and that takes them an amount of time, right? That they're telling us is 25 minutes to get ready. So once they're all ready, then they start pouring concrete, and then there's a cycle time for that. So they're going to lift it up, swing the bucket, pour it, come back. We're told that takes 10 minutes for each of those cycles. And then once they're all done cycling the concrete, then it takes 20 minutes to clean up and get out of there, right? So if you can kind of visualize that operation, it kind of helps in determining or calling out the relevant items that need to be calculated. So everything is based on how much cubic yardage needs to be poured. So what we're going to do is look at the number of buckets, the number of bucket loads that are required, right? So we're working with 110 cubic yards of concrete, and we know that the bucket will hold 2 cubic yards, right, per bucket load. So running those numbers, our cubic yardage cancels out, right? We're left with just bucket loads. So we're left with 55. We'll just call those buckets, right? So we have to swing that bucket 55 times. Well, that's going to dictate how much cycle time that we accumulate, right, as we're doing this operation. So if we say total bucket cycle time is going to equal 55 buckets times 10 minutes per bucket, right? We were told that It's 4 minutes to load the bucket and 6 minutes to swing the bucket, dump the concrete, and then come back for more, right? So this is our total cycle time with the 55 buckets. Pretty straightforward. We're going to come up with 550 minutes, right? And now we need to factor in the total setup and demobilization time, right? So that's the stuff that we're doing up front and the stuff that we have to do at the back end of the operation. So we're going to call that total setup and demob time. And we were told pretty straightforward that we had 25 minutes for setup. Then we're going to add our 20 minutes for teardown or for demobilization. So we're going to add 45 minutes to the operation for those items. So now we can figure out our total operation time. It's just adding that up, right? 550 minutes plus 45 minutes is going to be our 595 minutes. Okay. So that's the total time. Now, what we need to do is get things converted into hours, because now that we've got the total time of the operation, remember, we're trying to get at the cost, the labor cost per cubic yard of concrete. We know the cubic yardage, and our wage rate is given in terms of hours, right? $25 per hour. And so we need to convert this to hours so our units are consistent. So if I've got 595 minutes, I'm going to divide that by 60 minutes per hour. Minutes cancel out. I'm left with just hours. And that's 9.92 hours. And I would argue that that's close enough to 10 hours. But that's what we would round that up to in a practical situation, right? So let's round that up. Okay, now let's get into figuring. Now that we know how long we worked, let's apply the crew size that we had and their labor rate, and see if we can't get to a cost, a total labor cost. Okay. So continuing on, we have straight time worked, right? We know that the first 8 hours is straight time, right? So we can say that we had 8 hours, and that was times the 5 crew members, right? We were told we had 5 crew members, and their average weight was the $25 per hour. And so we times that out. And so our straight time looks like we're going to be $1,000. Okay. Now we went over, right, our 8-hour workday. It says that after 8 hours, right, the 1.5 times the regular rate starts kicking in. So we actually, since we went 10 hours, we've got 2 hours that are overtime, right, times 5-man crew times our 25 per hour times our 1.5 overtime factor, right? So that's a times there. And if we grind through that, we get 375 for our overtime. Sum those up, and our total labor cost is $1,375. Okay. Now back to the what the problem is actually asking. It's asking for a unit rate. It's asking for labor cost per cubic yard. Well, we know our cubic yardage, right? We now know our labor, so we can take our labor and divide it by the units that we've got, which is 110 cubic yards. And we should come up with $12.50 per cubic yard. Zoop. There's our answer. So the key to this, in my mind, as I worked through this, was just first of all visualizing the process, what's actually happening. That actually helps you calculate the time, the overall time of the operation. Then we could start applying that time to the labor costs, and figuring out what we had straight time versus overtime, and then dividing it by the actual quantity that we had executed, the 110 cubic yards, and we were able to come up with the right answer. So not too bad. It's just visualizing the process. Is there any questions on that one, Isaac?
There's been no questions that have been put into the chat, so I don't know if you guys have any questions about this one on how to do this estimate. Let us know and we can cover it. I could also envision that excuse me, I could envision that any one of these could be a question as well. We trickled this all the way down to the labor cost per cubic yard of concrete, but you could, maybe one of those problems could be just total operation time or things of that nature.
Yeah, they could ask you what's just the total labor cost for the operation, right? And then we would have stopped at the 1375. They kept going because it is a useful thing, because you could apply this as a heuristic or historical data for your next job, right? You could say, if you were estimating, you could go, well, on the last job, we paid $12.50 per cubic yard for our labor. I think that's probably about where we're going to be this time. And you could use that number for estimating.
Yep. Yeah, no other questions have come in. I think these are good construction problems. So,
okay, let's roll on to the next one then, shall we? So this one's a fun one with dealing with excavation and optimizing excavation operation. This one says an excavation contractor is planning the mass excavation for a new residential building. Excavated material to be exported from the site is calculated to be 4,000 cubic yards. The excavation work is initially estimated to require one excavator with a production rate of 60 cubic yards per hour, one loader with a production rate of 100 cubic yards per hour, and 3 dump trucks with a combined production rate of 30 cubic yards per hour. And to optimize the excavation, which type and quantity of equipment should be added to the operation? So, an interesting question. So the way to get at this thing is to look at the durations of each of these pieces of equipment. So we know they're digging a big hole. We know it requires one excavator. At least initially, they think it's going to be requiring one excavator, one loader, and 3 dump trucks to pull this off. And so what we need to do is analyze each piece of equipment and see what the production rates are going to generate as far as time or duration is concerned, and see how they balance out. And then we'll be able to make some decisions from there. So what we're going to do is we're going to look at the one excavator. And we were told that if we have to dig 4,000 cubic yards, that excavator is going to be able to tear through 100 cubic yards per hour, right? So we're taking a quantity again, and we're dividing it by a production rate, and we're going to end up with a duration, right? So, cubic yards cancel out, not the 100, that's still there. So if I take, and I messed up here, just realizing. The excavator had a production rate of 60, right? Not 100?
Yes, Anthony caught you on that, and he's typed 60.
Good job, Anthony. This is 60 yards per hour. So we calculate that and we come up with 66.67 basically, right? Hours, because cubic yards cancel out and I'm left with just hours. Now we're going to look at one loader that we were given for the operation. Do the same thing, right? We're going to take the 4,000 cubic yards that that loader has to tear through, and we're going to divide it by that piece of equipment's production. Right now we use the 100 cubic yards per hour, right? And we come up with 40 hours. And now I've got 3 dump trucks that we've thrown at this operation. And the combined productivity for those 3 dump trucks is just 30 cubic yards per hour. Okay. And so we can look at that. That's going to generate 133 hours of duration. So now that we've got each piece of equipment broken down, we can ask ourselves, okay, what piece of equipment is not being as efficient as it could be? What's taking the longest out of all of these? And it's obviously the dump trucks, right? If we only use 3 dump trucks and we're trying to haul out 4,000 cubic yards, it's going to take those dump trucks 133 hours. And so each dump truck is probably holding about 10 cubic yards. And it's probably a function of how far they're having to haul the material. It's taking them an hour to get a round trip done for wherever they're hauling all of this excavated material. And so it's taking a long time. So just kind of examining this, we can determine that the dump trucks have the longest duration, and they're the ones that need the adjustment, right? So just by inspection, you can see that if, let's say we added 6 dump trucks, we could say that those 4,000 cubic yards, we're doubling the number of dump trucks, so our production rate would be doubled to 60 cubic yards per hour. And if we did that, why then we're right at 66.67 hours, which is matching very closely to what the excavator is going to be able to load those dump trucks at. Looks like the loader is going to be sitting around a little bit, but we've optimized the operation as best we could because the dump trucks are going to be able to keep up with the excavator, and we've optimized the operation here by just adding those 3 dump trucks. So I would say after all of that, that the answer is 3 dump trucks is what needs to be added to the operation so that their production rate matches what the excavator is doing. Yeah, the loader is going to be sitting around a little bit, but if we were to add another loader and increase the production rate to 200 cubic yards per hour, this would just go down even lower, right? Technically, theoretically, this would go down to 20 hours, and that doesn't help us, right? That's not.
Would there be any point in getting your excavator and dump trucks down to 40 hours?
Yeah, that could be an adjustment. It's the underlying assumption that we're going to, that's a good question, Isaac. I mean,
I guess it depends on what you want to
usually the
spend.
loader's kind of pushing the material around and getting it stacked. So once the excavator's got things kind of stacked, the loader's just kind of pushing things around, and the excavator ends up actually loading the dump trucks. So if you look at just the operation that's happening, you're really most optimized if the excavator production matches the dump truck production exactly. But
Hey, Mark, there's a general question that came in that has nothing to do with this problem,
okay.
but about construction management.
Okay.
Does a construction manager, does their work involve site visits only, or site visits or office work only, or a mix?
It's a
And
mix.
what's the earning potential for construction manager? We got a guy, Dimple, is interested in becoming a construction manager.
Well, the earning potential is actually really good. In fact, engineers that are into the project management side of things um, actually fare a lot better than maybe an engineer that's in a design firm. So you might find a project manager, an experienced project manager is probably going to be, in the 120 to $130,000 a year kind of a range, and then that goes up depending on the size of projects that he's managed. But yeah, project managers. I mean, if you're a successful project manager and you're designing or you're managing multi-million-dollar projects, I mean, your salary can be 180, 200K a year for those guys. So it's a fairly well-paid profession, especially if you're someone with engineering, construction engineering as your background. Um, you
And it's a
can,
mix of office work and site visits.
and it is a mix of office work and site visits. So you're responsible for managing the entire. So you have a team of. If it's a big project, you'll have a team of superintendents that report to you. You'll have a team of project engineers that report to you. And then you're essentially the liaison. You're the interface between the project and the ownership a lot of times and the design team. And so you're kind of balancing the actual execution, managing the execution on the job, and making sure that your ownership, your customers are happy with how things are progressing, the quality, the schedule, and everything that goes along with that. So yeah, it's a big responsibility, and those guys are well compensated because it takes a lot of experience, but once you got it, you can be pretty well compensated for that.
Cool.
Is that a good enough
Any
answer?
any questions surrounding this question? If you do, leave it in the comments and we will get to it. But I
Okay,
think we're good to go to the next.
let's head to the next one then. Okay, so this one's a classic, a painting question. Okay, this one says, a painting subcontractor is estimating costs for painting a room. Consulting past production data, the subcontractor determines that each surface of the room to be painted will require the same material, productivity, and labor rates as listed in the following table. We've got our table down here. And then it says, what is most nearly the subcontractor's cost to paint the 60-foot by 30-foot by 12-foot rectangular room with two 6-foot by 7-foot doorways at each end? Assume paint material must be purchased in full gallon units, and a $200 allowance is required for painting the door casing and the room trim. So we've been given a table here that contains historical data from this subcontractor on a project that's similar to the one he's looking at, this room, the 60 by 30 by 12 foot room. And this subcontractor is saying, you know what? I can apply the same costs, I think, that I had before, same productivity rates. Let's figure out how much this room is going to cost. Okay. So first thing we need to do is what I would do is attack the ceiling first. So let's calc the ceiling area and material and labor costs. So the ceiling, if we've got a 60-foot by 30-foot by 12-foot room, maybe I'll draw a picture over here. So if you visualize this room, it's just a regular, we'll say rectangular room. And this thing's going to be, and it's not to scale here, obviously. Right? It's going to be 60 foot long. We're saying that it's 12 foot high. And I know I didn't draw this to scale very well, but it's 30 foot wide, right? And then it's saying there's a pair of doors. So we've got some doors here on this end. Oop. There's a door here. And then if you were to Visualize the inside of it there. We got another door over here on the other end. Kind of a visual of what we got going on.
Nice drawing.
Not the best drawing in the world. I'll admit
Looks
it.
good.
So let's work on the ceiling first. Okay. So we're going to say that ceiling, as far as the area goes, right, is going to be 60 foot times 30 foot. And we're going to come up with a total of 1,800 square foot for the ceiling. Based on our table, we're going to say that I'm going to abbreviate this. These are our material costs. They're going to equal our square footage divided by our coverage rate. So if we look at our ceiling, our coverage rate is 220 square foot per gallon, right? 220 square foot per gallon. And if we divide that out, we're going to get 8.18 gallons. But we're also told that the paint material has to be purchased in full gallon units, right? We can't go to the paint store and say, I want 8.18 gallons of paint. They're going to say, sorry, dude, you got to buy the full 9 gallons. So for the ceiling, we're going to need those full 9 gallons of paint. So we're going to take those 9 gallons, we're going to times it by the material cost at the ceiling paint, which was $41.25 per gallon. We times that out. And for the paint, we're at $371.25. Okay. So that's our material cost. Now for the ceiling, let's figure out what the labor costs are, right? So we're going to take that same square footage, the 1,800, and we're going to divide that by our production rate, which was 215 square foot per hour, right? I'm looking up here at my productivity. Okay. And then I'm going to take that. What that will do is if I divide that by the production rate, right? Square footage cancels out. I'm going to be left with hours. So I'm going to go ahead and times that by 38.50 per hour, which is also given in the table, right, as my labor cost. And it looks like I should come up with $322.32. Okay, so for the ceiling, I'm going to go 371.25 plus 322.32. So my total cost for the ceiling is going to be $693.57. $693.57. Okay, so that's just the ceiling. Now let's head on to the walls. Now that we kind of have the gist of the operation, right? We're calculating the area. We're applying our coverage rates to get our number of gallons of paint. And then we're using the same square footage, right? And then we're applying our production rate to find our labor costs. And then we're adding them up. Okay, so for walls, let's figure the area. So I'll go through this one a little quicker since we get the gist of it. This one's going to be 60 feet times 12 feet times 2 sides, right? So I'm taking the length of the wall times the height, right? Times 2 sides of the room. And I'm going to go times the other sides, which were 30 foot, times 12 foot, times 2 sides again. And then we got to subtract the area of our doors that are right here on the end, right? Those areas are a separate item. The doors are a separate item. So we got to subtract 2 times. Those doors were 6 foot by 7 foot. Nice big doors. Okay, so the area of our wall is going to be 2,076 feet squared. And again, doing the exact same thing. We're going to go calculate our material cost. We're going to say 2076 feet squared divided by 240 feet squared per gallon. Again, I'm looking at the walls now, and I'm looking at my production rate that I get on my walls. And I'm going to say that gives me 8.65 gallons. And we can't buy 8.65 gallons at the hardware store, right? So I got to bump that up again to 9 gallons. And so if I take my 9 gallons and I times that by my 41.25 per gallon, what do I get? I get my 371.25. Okay, that's my material. My labor, I'm going to take the same square footage, the 2076. This time I'm going to divide it by my production rate on my walls is 230. Square foot per hour, right? And then I'm going to take that, times it by my labor rate for walls, which I have at, looks like I'm slipping down here. Let's pull me down so we can see. I'm at 42.5, 42.50 per hour. Times that out, and we should get 383.60. And then now we can take both the labor costs and the material costs, right? This one and this one. And we can add them up like we did up here. So for up here, for both combined, we had 693. For this one, we're going to go 383.6 plus 371.25. And we're going to come up with 754.85. Whew. Okay, now I think we're done, but we're not because we haven't figured the doors yet. So rather than grind through that same procedure, I think everybody's getting the idea that we take each element, we get the area, we divide it by the coverage rate to get how many gallons of concrete, how many gallons of paint we need. We times that by the price, and we're grinding through those operations, and we can get the material and the labor costs. So just really quick for the doors, because this has taken a while to get to it. The doors, we've got 2 of them. We've got 6 feet times 7 feet, right? So we've got 84 square feet for that. And if we ground through the same operations, you'd see that for the paint, for the material, we'd have approximately, and I won't go through the whole calc here because you guys get the idea, 0.84 gallons, and we can't buy 0.84 gallons at the hardware store, so we need a full gallon for the doors. And then the labor, again, we're taking the square footage, divide it by the production rate, which on the doors it's a lot less. It's only 120 because doors are smaller. Takes a little longer as far as square foot per hour to paint those things. We're going to times that by our $43, and we're going to come up with, so let's see. So the 1 gallon, I didn't finish the material. 1 gallon on the doors is going to be $43. And then if you go through the labor, which is 84 square feet divided by the production rate, which was 120, times our $43 per hour. You're going to get $30.10. My writing's probably getting a little sloppy. We add those up. 72.4, $72.40. So that's the cost for my doors to paint those. And then now we just sum up everything that I've got bracketed. So
Sum that up, and what do you get?
if I sum up 693.57 plus 754 plus 85, this one's plus 72.4. And then don't forget the allowance. We have to have a $200 allowance for the trim, right? So add all those babies up. And we're finally there after all of that. $1,720.82. So kind of a long process, but straightforward once you get the gist of it.
I think that's a long problem, but I think when you practice that, you chug through it pretty quickly.
Yeah.
I guess some of the keys are to make sure to subtract out those doors and don't forget the allowance. So.
Yep. Trying to make a.
Cool.
Okay.
Any questions on this guy? If you do, leave them in the comments. We'll get to them. I say we jump to the next one.
Okay, off we go. Making progress. So this one's, we got a brick mason. He's trying to estimate a job for brick on the front elevation of an office building, and to accurately assess the cost, the number of bricks needs to be quantified for the front of the building, and it's measuring 200 feet long and 20 feet high, and 25% of the area is occupied by windows and doors. The owner of the building has requested that a standard brick measuring 2 5/8 by 3 5/8 by 7 5/8 be used in a running bond pattern using a standard 3/8 inch tooled mortar joints. So what is most nearly the number of bricks needed for this job? Okay.
This one always gets people, by the way.
Yeah, it's because it's the size of the brick, but if you think of the brick in a modular sense, so if we were to draw just one brick, the brick dimension, so 7 5/8 isn't a friendly dimension, but if you consider the mortar that's right on the end, if you were to color in the mortar that they put on the end of the brick, and then of course when they seat it on the brick below, they put a little layer of mortar down there as well, right? And so if you think about things in terms of a brick module, then you can say that I've got 7 5/8 plus 3/8. I got a full 8-inch module here on my brick length. And then my depth this way, if I count the mortar, is going to be 4 inches, right? Which is the 3 5/8 plus the 3/8. And then my height this way is going to be the full 3 inches, right? Because I've got 2 5/8 and I'm going to add that tooled mortar joint. So if we think of terms of the entire brick module as it's being placed, then I think it's a little bit clearer. Okay, so first thing out of the box, we're going to calculate the area of the building. So 200 feet, this is just the front of the building, front elevation. So we've got 4,000. And then we're going to remove the area that's occupied by windows and doors, right? And we were told that was 25%. So we're going to say that's times 0.25. We're going to subtract that from the total. So we're going to get 3,000 square feet of area that has to be covered by brick. And then to calculate the number of brick, we're going to take our 3,000 feet squared, and we're going to divide that by the area of the brick. So we've got 8 inches divided by 12 is feet, right? And then I'm going to say 3 inches divided by 12 is also in terms of feet. And again, I'm just looking at this area right here is what's covering the 3,000 square feet is just this hatched area that I got right here, including the mortar bed. Okay. So calculate that out and I get 18,000 bricks. A lot of bricks. Okay. That's it. Pretty straightforward.
That's it. So this one always trips people up, I think, because they're thinking about that mortar and the brick, and estimating kind of gets confusing for them. So
yeah, and
it's nice to see that.
If you just think of that in terms of a brick module, right? If you can.
What if the bricks were too deep?
Then you would have to times this by 2, right?
Sounds
and
good.
you'd get 36,000 bricks. That could happen if they were too deep.
Okay, any questions on the bricks? Gotta love a good brick problem.
Yeah, we love the bricks. Okay, next.
If you have any, leave them in the comments. We'll get to it.
Let's keep rolling. This one's going to be a roofing question. And so let's move up here a little bit. Framing contractor is trying to estimate the quantity of plywood sheathing required for the shown hip roof. And so just so everybody knows, I mean, this is the plan view on a hip roof, and a hip roof is opposed to a gable end roof. Has basically right a hip here, and we've got a ridge here, and then these side little things they call them hips, right? And that's a hip here, and those slope down to the edge of the house. Okay, so that's a hip roof.
Mark, the question came up on the brick problem.
Okay.
Will they specify H, W, and D for bricks versus WHD? I think people also get confused by the dimensions given.
All you have to remember is that the depth of the brick is the 4-inch dimension. The deeper dimension, the height of the brick is the smaller dimension. I don't know what else to say other than you just kind of got to be familiar with.
And the length is the longest.
And the length is the longest dimension. And then you kind of have to visualize how these bricks are going to get stacked. I mean, that running bond pattern everybody's seen, right?
Another question came up is there any chance on the PE or FE they ask for the quantity of mortar required?
That is a possibility. Yeah, and so what you would do is you'd figure out your total square footage that you needed, and then I would figure out the number of bricks, and you could subtract the actual 2 5/8, right, times the 7 5/8, that area, right? You could divide that into your square footage and get the area of actual brick area that's required, and then the delta, what's left over, would be the area of the mortar. And then from that you could times that by a depth, in this case 4 inches, and you could calculate a volume of mortar.
Good questions. Sorry, those came up.
All right, should we head back to the roof?
Yep.
Okay, so on the roof, we talked about it being a hip roof. Okay, it says, for the given dimensions, what is most nearly the number of 32 square foot plywood sheets needed to cover the roof if a plywood waste factor of 15% is assumed and a roof pitch of 8 to 12? Okay, well, we could be, this one kind of takes a little bit of a thought in realizing that a hip roof, the area of a hip roof is going to be the same as maybe what you see on a typical gabled roof. So if this ridge went all the way to the edge, we'd be calculating the same area, roof area, that we would on a gabled roof. And so that helps us streamline the operation. Otherwise, you're starting to think about, well, I got this area 1 maybe, and this might be area 2, and maybe this is area 3, and this is area 4. And I got to grind through the calculations for each one of those areas. And I've got a million triangles I got to calculate, and it gets really complicated if you're thinking of it in those terms. So if you recognize that a hip roof and a gabled roof have the same area, then we can take more of a cross-sectional area. So if I was to draw a little section sign here, and say we're going to take a section through this roof, and I'm going to draw it down here. So here's my gabled roof. Here's the bottom of it. And we're going to split this down the middle. And we're going to say that's 24 feet, and this is 24 feet, right? 48 divided by 2 is 24. And we're going to put a little dash line between there to split it. I could say, since I know that a gabled roof and a hip roof have the same area, all I really need to do is calculate the length of one of these sides and times it by the length of the roof. And then times it by 2 sides, right? I got 2 sides. I should be able to calculate the square footage of this thing. So just using the properties of triangles, if I say this is side A, A, B, and that's side C, we can get at this. And then I know that my slope right on my roof is 8 to 12. So I can use those proportions to go ahead and calculate what side B is going to be. And I think once I have side A, which has been given, and I can calculate side B, given these proportions, I can get at side C. And once I've got side C, then I just times that by the length of the roof, and we should be pretty close. So if I said that to calculate B, if I just use the proportion, if I say I've got 24 feet, and if I divide that by 12 feet, and I set that equal to side B divided by 8 feet. So what I've done is I've taken 24 feet is to 12, right? Because I'm working with a 8 to 12 slope. 24 feet is to 12 as 8 is to side B. I'm just creating a little... Yeah, similar triangles. I'm just creating a little proportion here that helps me calculate side B. So I can say side B is just going to be 24 feet times 8 feet, all divided by the 12 feet, right? And I come up with side B of 16 feet. So now I know side A, I know side B equals 16. And now we're just going to take the square root of the sum of the squares, right? To find side C. C squared equals B squared plus A squared, right? So I can say C equals 16 squared plus side A is 24 squared, and we can take the square root of that. And we're going to come up with 28.84 feet. Okay, well, now I've got the length of side C. I just need to times that by the length of the roof, and bam, we're there. So I'm going to go 2 sides times 96 feet times my 28.84 feet. And I'm going to come up with 5,537.28 feet squared, okay? Now we got to start going back here and looking at, okay, I got to figure 15% of that plywood is going to be wasted now that I have the actual square footage of the roof that I'm covering. And I've got to take into account that each sheet of plywood is only 32 square feet. And we have to buy plywood in whole sheets, right? It's like the paint at the hardware store. You have to buy whole gallons. So if I take our 55, 37.28 feet squared, and then I add the waste factor, which I have to apply to the area again. All right, that's times 0.15. I take all of that. So I've got my original square footage. I've added the waste, right, the additional that I need. And I divide that by my 32 square foot per piece of plywood. I get 198.99, which in all practical terms is going to be 200 sheets. We could say it's 199, but usually they sell sheets of plywood in bunks of 44, and so we'd have to look at that as additional. But you're looking at 200 to 199.
Cool.
The number of sheets. So that's how you get that one.
Any questions on the roof? These ones are always popping up, so good one to cover.
Yep.
Let's go to the next one, and if any questions pop up, we can jump back.
Okay, here we go. Last one. This one's a fun one. This one's construction engineering type stuff. And this one says a construction engineer is designing the supporting formwork and shoring system to hold up an 8-inch thick post-tension concrete slab during construction. The unit weight of the concrete, including the reinforcement, is 150 pounds per cubic foot. The engineer has selected an aluminum shoring system with adjustable steel shores that have an ultimate capacity as listed in the table below based on the shore height. If the 8-inch post-tension slab is to be constructed at a height of 10'6" off of the ground floor, what is most nearly the steel shore spacing required, expressed in terms of square feet, to safely support the slab and the required 50 pounds per square foot of construction live load and 10 pounds per square foot of formwork dead load. Assume a factor of safety of 3-to-1 must be maintained for the steel shores. So, holy smokes, how do we even attack this one?
You
Well,
give up and you guess B.
You could do that, but B might be wrong. No, the first thing we need to do, so we've got to get it the weight that we think is on, or what the weight of the PT slab and the weight of the construction live load and the formwork dead load, how that is being, I'll say, distributed to these shores. We need to get at that first. So to do that, what we need to do is let's just go ahead and take the weight of the slab, which was given to us, or the weight of the concrete, which is 150 pounds per cubic foot. And then let's figure out how much the concrete dead load is, right? We know the slab is 8 inches. And if we times that by 1 foot per 12 inches, I should have bracketed this out here. Don't look at that one. We come up with 100 pounds per foot squared is the load coming from just the concrete, right? Inches cancel out. I got a foot here. One of these cancel out, and I've got pounds per square foot. And then what I would do is add our construction live loads, which are required by ACI. So if I take my 100 pounds, I was told that I've got to add 50 pounds of construction live load. So that's 50 pounds. And then I've got a formwork dead load that I've got to deal with. So I'm going to add that as well. And so this is the combined load, 160 pounds per square foot, that is being essentially distributed into the shore. Now, we're given a table here that has shore lengths, right? And it gives us an ultimate capacity. So this is the capacity of the shore as it's about ready to fail. This thing's going to buckle and fall down. And just to kind of show what we're doing here, so here's our 8-inch. We'll call it our 8-inch PT slab. Here's our ground floor. And we've got our shoring system here. And what we're looking at is just, I'm going to draw these, even though these are steel shores. I'm going to kind of draw these as more like what we call Ellis shores. Right? So those shores are holding up the formwork up here. And then this is the 8-inch slab right here. And we're trying to figure out how much load these shores can take, right? We've just determined that given all of the concrete dead load and everything that's coming down, this is 160 pounds per square foot. So now we got to look at the capacity of these things, and we've been told that this height is 10'6". Okay. So we're going to look at our chart. Well, the range that we need is right here, right? 10 foot to 12 foot. And it looks like our ultimate capacity is 16,460 pounds. So that is what we're going to work with here. So, but given these are ultimate capacities, we need to factor in the factor of safety, right? So we're trying to see where the ultimate capacity is. What's the load on these shores at failure? And then we're trying to back that off. It's kind of an ASD, I would say, approach to the design. We're just backing things off by a factor of safety. And so if we take our 16,460 pounds and we divide it by 3 to keep our factor in safety, or our factor of safety in check, we're going to have 5,486 pounds per shore that's allowed, right? So if I take my 5,486, it's a 6 pounds per shore, and I divide that by 160, this is the weight coming down from the slab, including construction live load and then formwork load. I get pounds that cancel out, and I should get a 30. Oh, sorry, my pen just died for some reason. Here we go. I get 34.3 square foot per shore. And that's our answer. So we've got 160 pounds per square foot. We've got a support. We've got an ultimate capacity on our shore is 16,460. We divide that by our factor of safety to keep things safe. We determine all we can put in there is 5,486 pounds per shore. We divide that by the weight that's going into the shore, and we figure out the spacing of the shore is required in terms of pounds per square foot, right? Of 34.3.
Sweet.
So that's a nice little shoring problem there. Any questions on that?
Shoring? I haven't seen any pop in on this one. Good little problem to cover. Yeah. I think that's all your problems, isn't it, Mark?
That's it. That's the last one.
Sweet. I'm going to jump on and show our faces here real quick.
Okay.
There we are. So, guys, thanks for joining us today on some construction topics. There was probably more that came into us. We just did not have time to get to them. We try to keep these to about an hour because we want to keep your day open. But again, these will be downloaded and uploaded into our courses. So if you want to join the course, either the FE or the PE, go to civilFEreviewcourse.com or civilPEreviewcourse.com. These will stay on YouTube and our other channels for a limited time. Eventually they will be pulled down and put into those courses, and I will probably do that shortly. So
cool.
Mark, thanks for doing this. I don't see any other questions coming in, so appreciate you jumping on and doing this.
You bet. It was fun.
All right, guys, we'll see you later. We'll do another one next week.